So we started section 2.2 last time, and we were looking at sets kind of for the first time. And I'd like to just remind you of a bit of vocab that we'll be building on today, the stuff at the end in particular. We had sets, not this one, the next one. We had items that we were calling Venn diagrams, had these images that were rectangles with circles contained inside. The rectangle itself is what's called the universal set, and any of the sets that are contained in the universal set are drawn as circles inside. And then if it's the part that's not inside the circle, but you're still inside the rectangle, that's called the complement. And we had done an example of complements right here, which was if U is the set of all OBU students, A is the set of those who are graduating, describe the complement of A, and it would be OBU students who are not graduating. So building on that terminology, a few more pieces. We have something called a subset. So a subset is a set contained inside a set. So for all sets A and B, B is a subset of A if and only if every element of B is an element of A. And visually, if I were to draw this, I don't have a whole lot of space on this slide. I probably need to redo this slide. But if I were to draw this and this were my rectangle, it would look like sort of nesting circles. That's what it would look like to have a subset. So give me a second while I shift this circle inside the rectangle. So pretend like it's more circular, though it doesn't really matter, and it's inside. And then if we had a circle inside of it, that's a subset. So the way that this is being described is that set B is a subset of A, and it's inside of the universal set U. Okay, so if you go back to the definition, it says everything that's in set B, it looks like a blob, but everything that's in set B is also in set A. And you're like, well, yeah, I mean, it's the nesting dolls like at Christmas time. Now, it does not, that definition, preclude the idea that set A and set B could actually be the same set. Right? I gave you an example of equivalent sets last time, or equal sets actually. And the equal sets that I gave you the example of was if I said my family and my husband said my family, we're talking about the same group of people, right? Like our immediate family, same group of people. So we could say that my family is a subset of my husband's family, and we could say that my husband's family is a subset of my family. Even though it sounds funny, it's true. Because every member of my family is a member of my husband's family, and every member of my husband's family is a member of my family. Now, if we actually expand things so that it's truly not the same, we have something called proper subsets. So when we're looking at a proper subset, we actually have something in the larger set, visually that's what it looks like anyway, that's not inside the little circle. So if my husband were to say my family, meaning his immediate family and all the people he sort of grew up with, right? Like his family of origin, that would be a bigger set than just his immediate family. So his immediate family, the ones he lives with now, that we do life with now, right? We are a subset of his extended family, okay? And it is a proper subset because there are people in his extended family, his parents, for example, who are no longer anyway in our immediate family. A couple of notations, sorry, I left that blank. The notation for subset looks like this. So we've had set B, and it's a subset, which it looks like this. Looks kind of like a U on its side, or kind of like a flat C. So B is a subset of A. You'll notice there's a bar underneath. That bar underneath actually has this sort of connotation, if you think about it, it's meaning it could be equal. It didn't have to be, but it could be. It's almost like when we say that we're looking at numbers, say X is less than or equal to 7. Well, X could be 6, but X could actually be 7 and still satisfy that too, right? They could be equal. If it's a proper subset, you simply leave off the equal part underneath. And that's the notation. Now, if you have a proper subset, B is a proper subset of A, it's a subset of A as well. It's just a stronger statement, right? It's a proper subset, that extra adjective there. If we were counting the number of subsets, so if you were to take my family of 8 people and you were to make, sort of mini categories, like there might be the subset of people who share rooms, or there might be the subset of adults versus kids, or there might be the subset of boys versus girls, right? All these different sort of arrangements of smaller groups of people, those are subsets. How many different subsets could you have? Well, in this case, for the letter N, if you have N elements, then it's 2 to the N subsets. So for my family, There are 8 of us, which means there's 2 to the 8. It's a very large number, different ways that you can sort of subdivide and group family members in my home. One of those is the family, its entire family itself, right? An item is a subset of itself. It's weird, but it's equal, and it satisfies the condition, right? That says that every element is an element of the other one. And so if you exclude the whole family, so you're only talking about proper subsets, you simply subtract one of them off. So you'd have 2 to the 8 minus 1 if we were looking at subsets of my family. There is actually a typo on the next slide because the last time I taught this, there actually were 5 math professors at OBU, and there aren't anymore, so there's actually 4. So let's just adjust that so that it makes sense from a contextual point of view. So it says, consider the set of all mathematics faculty members at OBU. Note there are 4 of us now. If we want to know how many different subsets of the math faculty there are, then we have this formula that we encountered at the bottom of this other slide. So we take the number 2 and we raise it to the power of the number, in this case, of math faculty, 2 to the 4th. So what is 2 to the 4th? 16, right. So there are 16 subsets. All right, so, and oddly enough, the null set is a subset. All right, so if you talked about the set of math faculty, we'll talk about more subsets in a moment, or null sets in a moment. But if you talked about the math faculty who have grandchildren, right now that's none of us. Right? None of us have any grandchildren, so that would be an empty set or a null set. Or you could talk about the set of male math faculty members. There's only 1. Right? So he's a set of 1 if you describe it that way. So there's sets of 1, there's sets of 2, sets of 3, or there's the entire math faculty set of 4. If you remove from the discussion the entire group as a subset, and you're only looking at the proper subsets, you simply take 1 away. So we would have 15 proper subsets. Again, the null set's one of those. It's not a very interesting subset, but it is a subset because everything in the null set, which is nothing, is in the math faculty group. Yeah, Hallie?
So anytime it's a proper subset, you always take away 1?
Yes, proper subsets always take away 1, and they're really taking away the entire group itself as labeling it as a subset. Yeah. All right, if you go the other direction, for instance, you know how many subsets or proper subsets there are, you can actually find out how many elements there were as well. So suppose that you have a set about which you know there are 63 proper subsets. How many elements would be in the set? Well, proper subsets have this form, 2 to the n minus 1. So you can start with that. And it says that this quantity, 2 to the n minus 1, is 63. So that's the setup that they're giving you, written in math notation. And we're trying to figure out what n is. You can do a little trial and error, but what might be most helpful to start with is to add the 1 before you do your trial and error. 2 to the n equals 64. So you could try some numbers. It's got to be a whole number. I mean, you can't have a fractional number of elements in a set. That doesn't work. So if you take 2 to the 4th, or you take 2 to the 10th, or you take 2 to the 7th, or whatever, you're looking for what equals 64. And I see some of you using your calculators to try for numbers. What did you get? I think, Jenna, 6. 6 is right. So if you have 6 elements, you end up with 64 subsets or 63 proper subsets. Is what that correlation, what connection that makes. Any questions on that? All right. Example 7 and example 8, if you look at them, they actually look identical with the exception of this piece in the directions. Okay, so look them on your paper and see if you can see what I'm talking about. The directions are slightly different. The first one uses the symbols element and not an element. Number 8 uses the symbols subset and not a subset. Okay? So there's some issues that we have to deal with when we're talking about elements versus subsets. And these examples work really well to talk about all of them anyway. So I'm just using the same set of examples, not because they have to, just because I can. Okay? So if you take a look at the first one, what does that symbol mean? We talked about it last time. It's the empty set or the null set. In particular, it is a set. And if it is a set, it's not an element. So this symbol right here would mean that it is an element. And an element is not the same as a set. So if something's a set, it's not an element. It's just the way it is. So on the first one, it sort of fails by default because it's not even a set anyway. We can't even talk about it being a subset because the only way something can be a subset is if it's at first a set, and it's not, right? So the same thing for an element. It can't even talk about it being an element of something if it's not an element to begin with. It's a set to begin with. Now the second one, the number 15. The number 15 is an element. Now take a look at 15 compared to 4 in the curly braces here. What's the significance of the curly braces? Do you remember? It makes it a set. So the fact that this doesn't have curly braces means it's not a set. But the fact that this one does have curly braces means it is. So C fails in exactly the same way that A fails. It's not an element because it's not an element at all. It's a set. So this one fails. Now on part B and part D, we have to work a little bit harder because they're not in curly braces. They don't fail because they're sets. They may still fail, but they don't fail for that same reason. So what we want to do next is we want to see whether they actually are an element or are not an element because of what comes next. We know they're elements, we just don't know if they're an element of what comes on the other side. So over here, this is what we've talked about as set builder notation. And if it bothers you, if you don't like it or you're looking at it and you're like, I'm not sure what it means, remember what it's telling you is it's all x's where this equation holds and n is a natural number. So natural numbers look like this, right? 1, 2, 3, 4, and so on. So if I'm taking each of my natural numbers and I'm evaluating it into this equation, I didn't mean that. There we go, I was trying to highlight. If we're trying to evaluate it into this equation, all we're doing is we're replacing the letter n with the values that we're letting n equal. So when I plug in the number 1 and I multiply it by 2, I get 2. And if I plug in the number 2 and I multiply it by 2, I get 4. And if I plug in the number 3 and I multiply it by 2, I get 6. What numbers is this developing? These are the even numbers. So this notation is actually a notation for how to write even numbers. It's the natural numbers times 2. Is 15 an element of the even numbers? No. So it's an element, but it's not an element of what comes on the other side of the blank. So it fails, but it doesn't fail for the same reason. Now when you look at D, it's actually written out for us already, right? 2, 4, 6, 8, 10. Those are all the same even numbers. But this time on the left-hand side is the number 16. So is 16 an element of those even numbers? Yeah. So that one actually passes. It's an element.
I'm confused on D. How do we start doing 2, 4, 6?
So we took our natural numbers
Uh-huh.
over here.
Yes.
Wow, that was interesting. I don't know what that marker was. So we took these natural numbers because it says that they're natural numbers. And we're putting the natural numbers in for n because that's what the n is representing.
Okay.
So we put them in one at a time.
Oh, and 2 times 1, 2 times 2.
Yes.
3. Okay.
Yes.
Got it.
Great.
I was just going to say, an easier way to think about it could just be plugging in 15 for x, and then you divide by 10 both sides.
You can think about it that way. Yeah, so what you're trying to see, that's another valid way to think about it in terms of the individual element instead of the group of what they're describing. So if you're actually trying to take the x itself, that's not what I meant to do. Neither of that was what I meant to do. Let's try that. And you put the 15 in for x because what you're trying to see is whether or not that has the ability to equal it. Then if you were to divide 15 by 2, because the 2 ends on the other side, you won't get a natural number. You'll get a fraction. Yep, good point. Okay, so we're going to do the same question, but with different directions. The symbols that we're going to use now are subset symbols. Okay? Now, it's important to realize then that that automatically means 2 of these fail. Which 2 fail automatically? Yeah, the 15 and the 16, the ones without the curly braces. These are not subsets because they're not sets at all. They are elements. So these are not subsets. Now, the other 2 at least stand a chance because they are sets on the left-hand side. We just have to see if they're sets that are subsets of the other side. Now, the first one you get for free, I mentioned this earlier. I talked about the math faculty who have grandchildren, and that's none of us right now, right? So if you're talking about the math faculty that have grandchildren, that's the null set. The null set, by definition, because it contains nothing, is contained inside of the set that contains all the other stuff. So this one is always a subset. So you might actually make a note to yourself that the null set is always a subset of anything. Doesn't matter what comes next. Not at all. This is a subset of the set that contains the number 0. But it doesn't matter what's on the right-hand side. It's a subset. Now, C looks a little bit funny in the way that it's written. I've got the 4, the set with 4 in it on the left. And then I've got the set of 1 plus 2, 1 plus 3, 1 plus 4, and 1 plus 5. So really, the question is whether or not the number 4 is one of those things that's on the right-hand side. And it is. It's equivalent to the 1 plus 3. Now, if it were messier and you didn't like it, kind of like I was talking about with the 2n one, you could actually simplify what's there, right? You could go, oh, well, that's just 3, and that's just 4, and that's just 5, and that's just 6, and you could just write them out. But what you're looking for is you're looking for the number 4 here that's a set, because it's in the curly braces, to be an element inside of the set on the right as well. So that everything inside the set on the left, which is just the number 4, is also in the set on the right. And since that does work, this one is also a subset. Now, I didn't ask the question, but sort of just as an aside, because I don't have an example that does that. Let's say I had here 4 and 7. And I had this same thing right here, right, which is 3, 4, 5, and 6. It is a set, right, on the left-hand side. But it's not a subset this time. Why? Yeah, there's a number on the left, the 7, that is not in the set on the right. Yeah? So this one would also be not a subset, but not for the same reason that the other ones were not subsets, but rather because it contains something that's not in the other set. All right, let's take a look at a very cool principle that you've seen used before. You've used it, whether you realized you were doing this or not. It's called the fundamental principle of counting, or the fundamental counting principle in your book. If you have an event M, and it can occur in little m ways, and you have an event N that can occur in little n ways, then event M followed by event N can occur in m times n ways. So we used it last time when we were talking about creating, let me find it. That was it. The one-to-one correspondences of 6 people. And we said we take the first person and we group them with somebody, and there were 6 different ways of doing that, and then they exit the building. We take the second person and we group them with somebody else, and there's 5 ways of doing that. And if we stopped right there, there'd be 6 times 5. That's the fundamental principle of counting. Okay, that's what's at play there. So as we're looking at that one, let's do an example. The question asks, how many different outfits can be created from 3 shirts, 4 skirts, and 5 pairs of shoes? You can assume they match or they don't match. Don't really care. We're just creating the outfits, okay? So these are my different events. My events are choosing each one of these types of clothing and putting them together. So there are 3 shirts, there are 4 skirts, and there are 5 pairs of shoes. And the fundamental principle of counting says that if I multiply 3 times 4 times 5, I will have the number of ways and the number of different outfits in this case that I've created. What number does that give me? 60. So there are 60 different outfits. So don't say you don't have anything to wear in your closet. All right, a couple more fundamental principle of countings. Let's say you have 6 favorite stores in the mall. In how many ways can the following happen? So the first one says you only have time to go to 3 of them. So if we're not caring about the ordering, like that's not what's happening right now. Like how many different options do it? Like in other words, like it makes sense because they're beside each other. That's irrelevant to the conversation at the moment, okay? So how many different stores do I have to choose from of my favorite stores when I make my first choice? 6. And we're going to assume that we're not going to visit the store and then walk out and right back in. That's not what we're doing. We're talking about visiting 3 separate stores, okay? So after I visit the first store, how many different stores do I have choices of after that? 5. And then one more store, and I have 4. So what is 6 times 5 times 4? Yeah, there's 120 ways that I can choose. 120. Well, what if we get to go to all 6 of them? Well, I still have that 6, 5, 4, and then what would I have? Yeah, 3, 2, and 1. And if I multiply those numbers together, it is 720. Good job. There are 720 ways that I could visit all 6 stores. Okay, you're going to do something for me real quick, so don't write this one down, but I'm going to write you an example down. I already mentioned an example of a null set today. So the example of the null set that I mentioned is roughly created, in reference to my life, but it was about the math faculty, right? The math faculty with grandchildren. So I'm going to create for you a null set about my specific life, not the math faculty's life, and then I'm going to have you do the same thing, okay? So my null set that I'm going to use are the monkeys in my home. And no, my 3 youngest children don't count. That's why it's a null set, right? I can talk all about the monkeys in my home and how crazy they are, but there aren't any monkeys actually in my home, like legit monkeys. I don't have a pet monkey, right? So I'd like for you to take a second and do one for your life. And then after you write it down, compare with a neighbor and see what you got as a null set created for your specific life. Okay, fill in the blank for you. No. Remember, I just told you a minute ago that we could use the math faculty, like the subset of math faculty who have grandchildren.
Oh, okay. I thought you said like monkeys in your home talking about your kids, so I was like,
No.
ants in my pants.
You can do that.
I thought we were talking about
That actually would work. You can do ants in your pants. That will work, Gracie.
Okay.
The set of ants that are in Gracie's pants. There you go. Mm-hmm. Okay, share with a neighbor. What do you have? Just chat with someone real quick. Okay, so somebody share what you have. Emily.
Money in my bank account.
Money in my bank account. That's wonderful. Only if your bank account's actually 0.
It is.
Okay, there you go. Jordan.
Chicken in my fridge.
Chicken in your fridge. Right, okay.
Shopping.
Need to go grocery shopping. I did that just a little while ago. What else? Usually somebody says boyfriends in my life.
She said men in my life.
That's usually, there's always somebody who says that. So I heard over here somebody said boys in my math class. So yeah, so null sets, I want you to remember that null sets are a real thing. They're just describing something that does not exist in a specific context, okay? All right, so you guys have a chance to do group work now, and we will push pause.